Hi, everyone. It's a pleasure to be here. I wanted to start by thanking the organizers that invited me to give this keynote, and also thank the local organizers for hosting us in this beautiful Helsinki. It's the first time I'm here. I'm really enjoying it. So, thank you. So, I'm TAMAR EILAM. I work in this beautiful place that is called IBM T.J. Watson Research Center, and you can see some pictures that I included here. I've been working there for 25 years. I'm an IBM fellow and a chief scientist for sustainable computing. And the topic of my talk today can be described in 2 words, only 2 words. AI, efficiency, 2 words. There is also a very long title that Hubertus was too long for Hubertus to read. I'm not going to read it. You can read it from the program. But it's really about AI efficiency. And I hope that by the end of my presentation, you are going to understand at least why, as the chief scientist of sustainable computing, I dedicate about like close to 100% of my time to AI efficiency. Okay, so let's start. First of all, let's start with the basics. So we all know artificial intelligence shows remarkable capabilities in very diverse areas. Let's list some of them. So we have geospatial analysis, the ability to take satellite images and analyze them in order to predict climatic events such as floods, fires, and also to analyze crop and deforestation. Very important for sustainability. And an example is the model, the foundation model that IBM Research has pioneered together with NASA. Another area, accelerating the scientific discovery of vaccines for new viruses, of materials to replace unsustainable materials such as PFAS, very important area, especially in semiconductors, where we have a lot of PFAS material that is going into the manufacturing of chips. Third area, which is the one that is the most obvious, is productivity. So each one of us here, and I trust that each one of you has used AI and know what I'm talking about, because you can really use AI for like everything that you do, and it's gonna make you more productive. And you know, one example is code, right? AI for code. We're able to generate code, debug, and test it, and obviously it's not perfect, but it's proven to help us with the productivity of writing code. Okay, so what's the catch? The catch is the cost. So what is the cost of using AI in these areas? First of all, energy consumption increase. So you look at this graph, and it's very apparent what's going on. It's flat for many years. And by the way, that is the total energy consumption of all of the data centers. Why is it flat for many years, despite the fact that the energy, the computation actually increased by a lot? You know, one explanation is that we had lots of low-hanging fruits that we use, like automation, virtualization, cloud, and so on, that really helped us reduce, be more efficient in how we execute workloads, so we can increase the computation while maintaining the total energy flat. That's no longer the case. We see a very worrying trend of increased energy consumption from computation, and it's expected to get worse. Obviously, there is a lot of bad publicity around AI and energy. So you see here, the AI boom could use a shocking amount of electricity. AI is said to drive surging electricity demand. As the use of AI soars, so does the energy and water that is required. It's not just about energy, it's also about water, and so on and so forth. Okay, but so energy obviously becomes the bottleneck, and this is not only about environment. So it's not only because we love nature that we care about energy. Energy actually becomes the bottleneck, and I like to quote Amin Vadat from Google. that said that sentence in a keynote in US Plus 2024. He gave the keynote in the first day. I gave the keynote in the third day. I told him later, you gave the perfect introduction to my talk. And that's what he says. We do not care anymore about total cost of ownership. We care about the total power consumed by individual applications. And why is that? It's because they have enough money, I guess. They have a lot of money. But at some point, you're running your data center, you maybe even have more space. Maybe you can even buy more GPUs, and you have the space to put them. Where you're blocked is that you cannot get more energy from the power grid. Done. You know, there is no more, basically. So energy becomes the bottleneck. So it's a real problem. And this problem has two faces. I call it the two-head monster. Why two-headed monster? It's because on one hand, we see explosion in the size of models. And why is that? Is because the size of models is the easiest way. So making the model big is the easiest way for us to get them to perform in terms of accuracy. So just put more parameters, put more data, and this is your race to get more accuracy. So models are getting bigger, and the energy is increasing in a super linearly with respect to the size of the models. The second head of the monster is that it is the end of Dennard scaling, also known as Moore's law. And what that means is very simple. We cannot get the same amount of efficiency improvements that we used to get every 2 years by just shoving more transistors into a smaller area. That doesn't work anymore, and the reason is that we have reached the, basically the limits of physics. And you get into all sorts of problems such as leakage that I'm not going to go into. But we cannot do that anymore. So we cannot gain for free efficiencies every 2 years. We got to work much harder to run these computations more efficiently. So this is the two-head monster. However, energy is not the only problem, as we know. AI risk involves bias, hallucinations, and other harmful behavior. Lots of bad publicity about that as well, and I'm sure that each one of us here is aware of these issues with AI. Not going to go into that. But what I do want to know, I do want to talk about for a second, is I was curious about how the godfathers of AI think about the risk of AI. And it turns out that it's interesting. They agree only on one thing. And the thing that they agree on is that all three of them are very surprised, or surprised to different extents, by the progress that we have made, so by the current capabilities of AI, and by the pace of that progress, okay? So they're all surprised to different extents. What they don't agree on is how to mitigate the risk. So famously, you have Jeffrey Hinton that famously left Google and basically proclaimed that AI needs to be stopped until we develop safety mechanisms. The issue is that the train has already left the station. We cannot stop AI. It's there. Then you have Yoshua Bengio, and his approach is to advance strong AI governance, okay? Like we're doing with the nuclear program, do it with AI. And the issue here is that governance, first of all, the government is way behind in terms of understanding the technology with respect to where they should be. Secondly, standards take a lot of time. And the technology is making such a fast progress that it's really lagging behind. And then lastly, Jan LeCun advocates openness and transparency, you know, versus secrecy and monopoly. So this is his approach to deal with the risk. And The issue is that it's not enough to, or it's not enough, so it's hard to get openness and transparency when running AI is so costly. When only very few can actually train these big models, how are you going to have openness and transparency? Who is going to force them? Doesn't work this way. So in order to have openness and transparency, and in order to level the playing field, so it's not going to be only a very few players in a monopoly kind of mode, but it's going to be everyone, a community, then we need to reduce the cost of computing with AI. Computing with AI, I mean training, fine-tuning, inference. So how do we make AI more efficient? That's the question, and this is the question that I'm here to answer. Okay, so AI efficiency, that's the topic. I hope I motivated it. Let's first define what it means. So the way I'm defining it, AI efficiency is the ability to run more AI computation, very simply, with less resources, right? Less GPUs, less cost, and less energy. And obviously, with acceptable performance, because you don't want to injure your accuracy, and you also don't want to have unacceptable latency, because nobody's going to use it. Okay? So that's the high-level definition, and we're going to go and dig into it a little bit later in the presentation. So the way I'm thinking about it is, in order to make AI efficient, we need a full-stack approach. There is no silver bullet. So what we need to do is focus on AI models, on the AI platform or control plane and runtime, and on AI systems. And my focus is really the AI control plane. But before I will go there, I want to touch quickly on the other layers, because there is so much really, really interesting research that is happening in each one of these layers. So starting with AI models. So the thing is, what did we say before? We said you gotta make, the easiest way to get into performant AI is to throw more money into the problem, which means more parameters, more data. Well, that doesn't scale. It's not sustainable, right? So we need to find better ways. So what do? This is really about AI model architecture innovation. We need to break the monolith, right? If we have monolith that is a behemoth monolith, then that's going to cost a lot of money and energy and so on. So how do we break the monolith? Well, I want to mention two different works that we did in IBM research. One is not exactly about breaking the monolith, but it's about going beyond the transformer-based architecture. So everybody knows transformer-based architecture. There was this famous paper, Attention is All You Need. Since then, everyone are focused on transformers. And transformers are generally, obviously, amazing idea. But the limitation is that it's quadratic in the sequence length. Because it's autoregressive, there is a sequence length, you're generating KV vectors, and that computation is very intensive and quadratic. So it really doesn't scale when you are increasing the sequence length, which is the queries that you're sending to the LLM. That's the sequence length. It's the size of that these queries. And you know that one of the use cases is, for example, document summarization. You may send 5 documents to this LLM. So this is a lot. The sequence length may include a lot of information. Okay, so how to approach it? So there is an idea which has been there. It's not actually a new idea. It's an old idea. It's called state space models. And the idea there is that you propagate selectively and you forget selectively, so you maintain an inner state of your understanding of the world, which has a fixed size. Okay? Very different idea. And what we did in IBM research is that we took that, idea, and we trained a model that is based on that idea using a lot of data, trillions of tokens. We also did other improvements such as quantization, and we made it work on VLLM, and indeed it performs much better. Another idea that I want to mention is the idea of mixtures of experts. So we talked about breaking the monolith. One way to break the monolith is to break it to smaller experts that are really good in multiple different domains. So you have one for knowledge, one for math, one for knowledge extraction, one for math, one for different domains, and they collaborate. So in every query, you may invoke multiple domain experts, but a subset in order to answer this query. And because the energy and compute is super linear in the size of the model, breaking the monolith to smaller experts can help improve. And again, we did some work here. And when I say we, I mean IBM Research. I'm representing IBM Research here, which is called self-MOE. Self-MOE is the ability to do that to take a monolith and decompose it to experts with much less work when the synthetic data is generated for you, is automatically generated for you. So you can read about that. I'm not going to go into details here. So this is about models. Okay, and by the way, I am just really talking about the tip of the iceberg in terms of the amount of work which is being done, but I'm giving you some ideas, and I want to tease your appetite. Specialized systems. So remember, we talked about the problem with Dennard scaling, right? So we cannot stay with general purpose CMOS anymore. That's not going to give us the results. What do? We move to specialized systems. Specialized systems are systems that are architecturally simple. So you simplify the architecture of the chip, meaning that the overhead is reduced, so it's more efficient, but it can address only a class of computations. Not all the computations, it's not general. It can address only a class of computations. So the obvious idea is to work on an AI chip. That's something that we did in IBM Research, and it's based on, years of research. So one idea is approximate computing. You present numbers with a smaller number of bits. And turns out that when it comes to AI, you can do that without losing accuracy. So years of research, they're summarized in that graph here that talk about approximate computing. Another key idea there, really interesting, is the asynchronous data flow. So if you look at a GPU, for example, the GPU architecture, there's a memory hierarchy there. That memory hierarchy is a lot of overhead. And what we did with the Spire AIU is have a flat memory, which means that it's much simpler and much less overhead. And it will work for AI. It will not work for everything, right? And indeed, the overhead is much smaller, so that means it's more efficient. And we got some very good results. So for some workloads, for some models, this is specifically for embedding workloads, you can look at the upper table. That's one thing that you can do, but how do I don't know how to do it, but never mind. You can look at the upper table, that's one thing, but the lower table is actually more interesting. So the upper table looks at throughput. The lower table looks at throughput per watt. So this is your efficiency metric. How much throughput? Throughput is work. How much work can I do with every watt? And it turns out to be that we are 8 times better than the H100, and 5 times better than the L4, which is more efficient than the H100. So, so you see here the numbers. There is different numbers for different sizes, but this is what you're seeing. So indeed, a huge improvement to the throughput per watt of the system, which basically is an efficiency measure. Okay, so as I said, I'm really just scratching the tip of the iceberg. There is so much work that can be done in these areas. And one work that is really exciting is how do we co-design model architecture and system architecture. Fascinating. I'm not doing it, but maybe someone here is interested to do that. But as I said, I'm going to focus on the AI control plane. So AI control plane, I'm going to specifically talk about the role of the control plane for efficient inferencing. So why inferencing? Why am I focusing on inferencing first? Why not training or fine-tuning first? And I think we should focus on the three of them, but why inferencing first? So the reason is that what we're seeing in the last year or so is that the computational burden is shifted from training to inference due to recent trends such as inference scaling, or also known as test time scaling, and chain of thought. So what's going on here is that, let's say I am more, my brain is more slower than a wrong brain over there, or maybe I'm a little bit slower or more stupid than Ron. What am I going to do if I want to solve a problem? I'm going to just spend more time working on that problem. At the end, I'm going to solve it, right? And how am I going to do it? So one way to do it is to try several times and pick the best answer, right? So that's inference scaling. Another way to do it is just to think for a long time, chain of thought. So I'm thinking and I'm getting to some intermediate result, and then I think more and I get to some intermediate result. So that's chain of thoughts. It makes sense. It just makes sense, right? But the effect is in inference is that if you get a query, you don't just start generating the outputs and sending them back. You generate a lot of tokens that are basically circulated that are not going out. And multiple, not transactions, but multiple responses like this. And at the end, you're generating a result. So the effect is much more computation at inference time. The burden is shifted to inference. That's why we're focusing on inference first. And then there are even results here from Gartner that say that 80% of data center workload accelerator will be specifically deployed for inference as opposed to training use. Okay, so that's why we're focusing on inference first. Okay, so I said I'm going to focus on AI control plane, but what is an AI control plane? So AI control plane is the glue that connects a diverse set of models and a heterogeneous set of accelerators, right? And here's the justification. We said it's not going to be one size fit all, and I justified why it's not going to be one size fit all before. I said beyond transformers, mixtures of experts, and so on. So there is a diverse set of workloads, Bamba, and so on. And then I also justified why we need a lot of different accelerators, right? And I'm even going to justify it more later. But it's not going to be one size fit all, because sometimes you need the Mercedes to drive, right? And maybe you need it because you're training a very, very large model. And sometimes you need something which is simpler but more efficient for the workloads that you have, okay? So you're going to have multiple accelerators. And the control plane is the glue that connects the models and the accelerators. So it controls every part of the execution, where to place them, how to schedule requests, how to configure them, and so on and so forth. Okay, so that's the control plane. So now the question is, what do we want from a control plane? And the basic answer here is we want it to run more with less, right? We talked about it before. The efficiency, what is efficiency? Run more with less cost, less resources, and so on. But what does it translate to when we're dealing with AI? What does it translate to? So first of all, maximum overall throughput, that's the amount of work you do, right? How many requests per second can you serve, right? Two, minimize latency, because that's the perceived performance of the user. The user is not going to stay with you if the latency is not good. When it comes to AI, we need to break latency to two different things. One is the time to first token, which is the time until you get the first token of the response, right? And people want to get it quickly because otherwise they lose patience, and we know that. The other one is inter-token latency. So now you're starting to generate these tokens one by one. You don't want to wait too much between every token, okay? So these are the two things that are important to pay attention to in AI. And then obviously The first, the throughput, is negatively correlated with the latency. Why? Because if you're shoving more requests that you're serving in parallel on an accelerator, because you want to do more work and more throughput, that will affect your latency. You're not going to be able to give enough resources to serve every request. So they're negatively correlated, and that gives us the definition of what we're trying to solve, which is how to maximize throughput, the amount of work, while meeting latency constraints. So I want my latency to be less than this or less than that. This is my constraint, okay? And we can further define some sub-goals, such as how to minimize dollar per token, because it's not just about the latency. I also want to minimize how much I'm paying for these accelerators, right? And we can also talk about how to minimize joule per token, or how much energy do I use to generate each one of these tokens. And when you look at these three goals, what's the relationship between these three goals? So they're definitely correlated. So if if I'm focusing on my yellow goal, it's very likely that if I'm trying to maximize my throughput while minimizing latency constraints, I'm also going to use less resources, and if I use less resources, I minimize the cost, I minimize the energy. But they're not perfectly correlated. Why? Because I have a choice what accelerators type I'm using. Some accelerators are cheaper, and some accelerators are more efficient in terms of the energy. So it's actually important to talk about each one of these goals and to look at all of them and see how we are meeting them. Okay, now why is it challenging? That's the question. So everyone here, you guys are from cloud, so you know that. If you're like me, I'm working in IBM for 25 years now, and we've been there and we've done it, right? In terms of optimization, we know about bean packing, we know about load balancing, round robin, and all of that. But we did it for microservices, for cloud native technologies. Cloud native technologies are very different. The first difference is that they're much more cheaper to execute, 3 to 4 orders of magnitude more QPS for microservices workload rather than AI, okay? And if they're cheaper to execute, then nobody cares about the optimization. And I've been there, I've lived that. Nobody cared about the optimization. Why? Because it's good enough, okay? That's not the story with AI. Now, suddenly, it's very expensive. But it's not only that it's very expensive, it's also much more complicated. Okay? So why is it more complicated? Multiple things. One, variable size of requests, inputs and outputs. Every request is different. The input is different. Sometimes I just ask, okay, 10 things to do in Helsinki, right? And I get a response. And sometimes I give them 5 documents and say, can you summarize it for me? Or what's the difference between this? Do research for me, Summarize the differences between this and that, full documents. So that's the input. But then the output is not even correlated to the input. You can have input that is very short with very, very long output. And it's not predictable. So lots of variabilities in the inputs and outputs, which is very much has to do with how much computation you need. Very much. 2, variable SLOs. I have workloads that are very different from each other. If I do auto-completion for code, I want to get the latency really quickly. I want to get a response, because otherwise I'm losing my patience. I'm writing it myself. I know what it is. It needs to be quicker than my typing speed, right? But if I, again, do document summarization of what, it can be slower. Even if I do help desk chatbot, it could be slower because it needs to be in the human pace of conversation and so on. So very variable SLOs, very different requirements. Resource heavy, okay? So they require a lot of resources. We talked about the pre-fill, where it's, the sequence length and the generation of the KV vectors and so on. And hardware affinity required, we're going to get into why hardware affinity is required. We're going to get there. But these are very, very different characteristics that make the problem more complicated. So before we get into how we're solving that problem, let's look at the anatomy of a single inference job. And what you need to know is this. Every inference job has two phases, prefill and decode. Prefill, you get the request, and for every token, in order, you need to generate a KV vector. And it doesn't matter what is KV vector right now, really doesn't matter, but you need to generate KV vector. And then the next token, the generation of the KV token, will depend on the previous ones, okay? And there are techniques to accelerate that and to do some things in parallel and so on. We're not going to go into that. But what you need to know is it's a very compute-intensive task to generate all these KV vectors, and that will govern the time to first token. Because before you generate the entire KV cache is all of these vectors together, yeah? You're not generating your first token that is the reply, okay? So that will govern the time to first token. Now, what do you need to know about decode? First of all, decode starts after prefill finishes. That's the first thing to know, okay? And secondly, it's because it's autoaggressive, it's like one by one, one by one, one by one. So it's the memory is the bottleneck, okay? And this is why we have techniques such as continuous batching. But continuous batching is parallelism across multiple different requests. So you're taking all these requests together and you're handling it, okay? So this is why the memory is the bottleneck for decode, but the compute is the bottleneck for prefill. And then the decode phase, that will govern your inter-token latency, okay? So now when you're generating the tokens, every token takes time. That's your inter-token latency, okay? So it's very important because any optimization that you do for inference relies on this understanding. Okay, so now the question is, what do we already know about inference optimization? So there was a tremendous progress in the last couple of years, tremendous. And I have sort of a short summary here. First of all, the idea of disaggregation. So you have prefill, you have decode. Because they're so different, you don't want to run them on the same accelerator. Why? Because they require different things. This requires compute. This is the bottleneck is the memory. They require different optimization techniques, and they scale differently. Because sometimes the output is very long, so you need more in decode. Sometimes the input is very long, so you need more prefill, okay? So the simple idea of this aggregation is I'm running prefill and decode on two different accelerator types, accelerator instances, okay? Next question. Okay, so we know that creating the KV vector and the KV cache is the entire thing is very compute intensive. It's a lot of work. The obvious idea here is instead of recomputing it every time, cache and reuse, okay? It's a very well-known technique from computer science, right? Cache and reuse. And this is only going to work if you have similarities between requests, right? Because if you cache something, but nobody else uses it because they don't have the same situation, then you didn't do anything. So my first question when I thought that is, okay, but what is the similarity? Turns out that there is a lot of similarity. Why? Because you have prefix. In every request, there is a prefix which is similar across different requests. And you only need, so because of how it's generated, you can always take a subset of the KV cache if it's in the beginning. Okay? And that's because of how it's generated. It depends on the previous ones, but it doesn't depend on the next ones. So it doesn't have to be a perfect match. If it matches the beginning, that's fine. You can take the beginning. So prefix is similar, so there will be similarity. There will be similarity in multi-turn requests. There will be similarity in rank-based use cases where you have documents that are basically summarized as a KV cache vector. Okay? So instead of recomputing, we're caching and reusing. Basic idea. Okay, so the next question is, but what about reusing across multiple servers, right? Because now, if I'm caching and reusing it, but the cache is only on one server, I'm sending all the requests to that one server. That server becomes way too overloaded, and other servers are not utilized. So I want to be able to share the cache across servers, right? So distributed KV cache management, that's the next idea. Next, okay, so if I have distributed KV cache management, that all relies on the ability to schedule requests to where the KV cache is. You have the scheduler, I get a request, it needs to go to where I know the KV cache is. So there is a scheduler there. The problem is with scheduling is, what about fairness? Because now that I'm sending all the requests to where the KV cache is, I give priority to requests for which there is a KV cache hit, right? And then I can starve other requests. So we need to balance it with fairness. So this is all about queue management, fairness. Next, okay, so what about the SLOs? I have different SLOs. This is interactive, this is batch. How can I manage them together? Again, queue management. And then what about reducing the cost? I have multiple different accelerators. Some of them are much cheaper, like L4. So can I use that, send to L4 rather than H100 if it's not going to injure my performance and save cost? So this is how to leverage heterogeneity for reducing the cost. What's the bottom line? I mean, and again, this is just the tip of the iceberg, hundreds of papers. I have only like about 7 here, right? Dimensionalities. Look at all of these different dimensions that you need in order to optimize inference. All of these different dimensions, right? And the question is, how do you know what to use when you have all these workloads, all these different characteristics? In one situation, you get these workloads. In other situation, you get these other workloads, right? And I'm giving some examples here. And then you have all these global objectives, cluster-level objectives, such as my effective throughput, also known as good put, the overall cost, and so on. Maybe there are different constraints. Maybe there is an energy constraint, and so on. And how do I know what technique to use? Also, how do I know what combination of techniques to use? Okay, because it may not be one, maybe 2 or 3 techniques that I need to use. And is it even going to work together? Was it tested together? Is it maybe going to contradict or conflict? We don't know. Okay? How to solve this problem? So now when we rethink the role of the control plane, we talked about a control plane, we talked about the obvious thing that we want to optimize. But let's think a little bit more what we want from a control plane. We want to consistently integrate multiple optimization areas and techniques. We want to allow maximum flexibility to adjust and tune based on workload needs, SLOs, and platform goals. We want to allow quick evolution and experimentations with new techniques. So I just talked about what happened in the last 6 months, right? I can assure you there is going to be more techniques coming, and I need a platform that I can quickly start evaluating it, and evaluating it with respect to other techniques and with other techniques, right? Simplify operational complexity, right? Enters LLMD. So LLMD is a project that we launched, and it's very, very new. It's a control plane for distributed inference at scale. And we launched it together with several contributing partners. So this is Red Hat, with IBM Research, with Google, with NVIDIA as a contributing partner. And then there are multiple other partners that joined us, such as Hugging Face and Intel and AMD. In fact, I think multiple contributors here in the audience, Chen and Danny, and several contributors that are sitting here, which is really nice. So we launched that project about a month and a half ago, and it's very nice to see this organic growth. So lots of stars and a lot of popularity and a lot of companies that are joining us. And basically, in the spirit of openness, transparency, and leveling the playing field, we're all working together to solve this problem. how to get to operational efficiency of AI so that everyone can play, not just the monopolies, everyone can play. That's the idea. So this is from the announcement, and there are, as you can see, we started with multiple different capabilities that we're putting here together. It's based on VLLM, pre-fill and decode disaggregation. We talked about what we need, key value cache offloading, Kubernetes-powered clusters and controllers, AI-aware network routing, and high-performance communication APIs. And I'm going to focus on these two here in my presentation. And one of the main ideas is, as we discussed, to take all of these optimization areas and to put them together in a uniform architecture. And this uniform architecture helps you operationalize, gives you the flexibility to test different techniques, and the performance. Okay, so that's the key thing. Have modularity, right? So a plug and play kind of thing. Have operational simplicity and actually do something to optimize. Okay. Right, so you see all of these areas. So let's just drill down a little bit and understand what we're doing there. So first of all, disaggregation. We talked about why disaggregation is important. You have prefill, you have decode. They have different characteristics. So what you want is to be able to select the accelerator type for each one of them. And you want to have the flexibility of scaling the number of instances separately for prefill and for decode. Because sometimes you're going to need a lot of prefill accelerators and a few decode accelerators. Sometimes you're going to need the opposite, a lot of prefill, a lot of decode, but a few prefill accelerators. So this will give you that flexibility. And the way we're doing it is that you have the inference scheduler and you have a routing sidecar, which is attached to each one of the VLLM servers. And dynamically, the scheduler decides on two things. It decides on a prefill deployment, and I say deployment, not accelerate, because it could be a few accelerators, and it decides on a decode deployment. And then the request is routed to the prefill. Once prefill is done, the request is being routed to the decode through the sidecar, and then the decodes begin. And as I said, the basic idea is you separate the two. That's good for resource allocation, utilization, scheduling, and so on. And it's also easier and more predictable to meet your time to first token goals and your ITL goals. Because if you see that the time to first token starts deteriorating, you know what to scale. If you see the ITL starts deteriorating, you know what to scale. So it's easier to manage these two metrics. Okay, so the other capability that we discussed why KV cache is important. And in LLMD, we're doing KV cache management. We're using LM Cache as the KV cache engine. It's another open source project. And what we have is we have a cluster-wide indexing. So all of the KV caches are indexed across the cluster to allow sharing between nodes. We're also doing offloading to enable cache reuse. So from the GPU, it can go to the CPU or to an external network-attached memory. Yeah, so enable KV cache-aware routing is another thing. I said it's not going to work without routing and scheduling being aware of the KV cache, because you need to route a request to where the KV cache exists. So that's another thing we did, and this is here. So here we're talking about a project which is called Gateway API, which we're using in this in LLMD. We're reusing. So Gateway API includes the concept of an endpoint picker, which basically, as its name alludes to, picks the instance that the request is going to. Okay. The nice thing about it, it's extensible, okay? So what we did is we're using the extension points in order to implement scorers. And scorers is the thing that selects the instance to be executing a particular request. So we've implemented multiple different scorers, session aware, KV cache aware, and load aware. To help us pick up and balance, also balance, for example, KV cache with utilization. Remember, we talked about that. We don't want to send everything to the same node if the utilization is too high and is too low somewhere else. So balancing all of these requires different scores and a weight function. And then we also extended it to have PD scheduler. So what is a PD scheduler? Remember, before, a scheduler only picks one endpoint, but with PD disaggregation, prefix decode disaggregation, you actually need to select two endpoints, one for prefix, one for decode. So we created this extension. And this is the basic capabilities that we have in the first release, which took us about seriously, it was a huge effort that we did in like a matter of 6 to 7 weeks. We just got together, and when I say got together, it's not one company, it's multiple companies working together. IBM Research, Red Hat, Google, and so on, to get to this minimum viable product, okay? That includes these capabilities, and we're already getting really good results. So what you're seeing here is, and let me see, you have this is specifically focusing on the scheduling aspects and also KV cache. So you enable KV cache, and you look at the scheduler, and you first of all use round robin, which is like without KV cache awareness. But then the other one, and that's the blue line. But then the other one, the red one, is when you're using the score and that is aware of KV cache and load and so on. And you see that the average inter-token latency and the average time between tokens is way lower, and the throughput is going up much more. So this is good results. And we have some more results here, but I'm not going to go over all of them. This basically talks about the amount of work that you can do without injuring your latency. Okay. So the thing is, and this is what I like to say, the release is always the beginning of the journey, right? So it's really just the beginning of the journey, okay? What's next? One thing that is very dear to my heart, because I'm actually intimately involved in, is autoscaling. So what is autoscaling? Autoscaling is the ability to change the number of instances, the number of accelerators that are allocated to a particular model, the number and types. Okay, so I have a model running, and how many accelerators being used and what type of accelerators being used, and can I change it dynamically based on the load and the characteristics of the traffic that I'm seeing. That's autoscaling. And obviously, your goal is you may have multiple global objectives. So here is just an example. Maximize throughput while maintaining latency within 20% of the target. That's an example of global constraints. Obviously, global constraints can be more complicated than that, and they may include multiple different objectives that you're trying to meet. Okay, so how are we doing it, or what are we working on? We have that concept of a variant. What is a variant? It's a model type. It basically describes a deployment. A deployment is a model type. It's a purpose. It's either prefill or decode, right? It's an accelerator type and number. Why? Because some models require more than one accelerator instance to run. They require at least 2 or sometimes 4. So it's an accelerator type and the number, and it's a configuration. So the tensor parallelism, the amount of tensor parallelism that I'm doing could be 2, it could be 4. It's the batch size maximum, which is another very important parameter, and could be other parameters. But this describes a particular deployment. So what's the idea? The idea is, in our world, at any given point, you can have multiple different variants. You can even have multiple different variants running the same model. So the same model may have, first of all, the accelerators for prefill and decode, and these could be different accelerator types and different configuration. But even for prefill, they can have different accelerator types. And the reason why you need it is in one of the papers that I mentioned above that deals with cost, okay? Is because you can have an A100 and an L4, and that allows you to have really to optimize the cost and just use what you need, okay? So you may have multiple variants, even for the same model, running at the same time, and the result and the idea of the auto-scaling is that you dynamically change the number of variant instances running in the system. Okay? One thing that is really important to understand, because people get confused about it all the time, is that the scheduler and the autoscaler must be loosely coupled. Otherwise, we're going to get into complicated situations. Scheduler routes requests. So what the scheduler knows is, this is my inference pool. This is the instances that are available to me right now to serve this request. And among these instances, I'm selecting the best one. It's not making decisions about how to change about changing the number of instances. Changing the number of instances is the autoscaler. So the autoscaler works in much smaller frequency, right? So it can be invoked every few minutes, maybe even every 10 minutes, and decide, okay, this needs to go up, the number of accelerators here needs to go up, this number of accelerators needs to go down. Scheduler needs to work really quickly. For every request, it looks at what is available, makes a decision. Autoscaler looks at the traffic pattern, look what it's getting, looks at the state of the servers, and makes a decision about increasing or decreasing the amount of resources that are allocated. So if we look at this, it's in the architecture, but when we launched it, we didn't have an autoscaler. So we're working to add an autoscaler, and the autoscaler is based on work that we've done in IBM research before. So we had something, and this something control, it includes several different components. There is a controller, it's a Kubernetes controller. The idea of the controller is to run periodically and synchronize the desired state with the current state, which is how Kubernetes works, right? So you define a desired state, you have your current state, you synchronize them. How do you do that? So you have a collector that collects all the metrics. Collector is not only about the VLLM metrics, it's also about the queues, it's also about the traffic patterns that you're seeing, so getting it from the inference scheduler. It's looking at the entire world, okay? And then you have an optimizer. The optimizer, after it looks on the entire world, it makes these decisions on where to add, where to decrease the amount of resources. And then the actuator is responsible for actually affecting the change. If you're familiar with the Kubernetes world, this can be done in multiple different ways. You can change the number in a deployment object, and it's just going to synchronize because that's how Kubernetes work. Or you can change a number in Prometheus that is picked up by a low-level autoscaling mechanism such as HPA. I'm not going to go into these details because it doesn't matter. There is an actuator mechanism, and it actually does matter, but it's a topic for another complete presentation. But there is an actuator there. And if you look a little bit about the optimization, what we do, so the way we think about it right now is there are actually 3 different functions. The function in the middle, model and variant, I like to call it actually variant optimization. Variant optimization is looking at each variant, so specifically at a variant, a single variant. Remember how I defined it, right? And it looks at what's going on there, and it understands what could be the maximum service rate and other parameters, and based on that, it recommends number of instances for that variant, okay? And then there is a global optimizer that looks at all the variants, and now, based on the global objectives, decide actually who is going to get what, because you may have resource contention, so you can't give everyone the ideal number, okay? So the global optimizer is based on so the first one is based on queuing theory, the second one is based on multiple integer linear programming. So that's the global optimizer. The third component is the model tuner. So I said that this is based on queuing theory, right? And queuing theory has parameters. So it basically looks at the curve, how the curve changes, latency and throughput, and understands when is the right time that you're not going to get any more, that you sort of actually reach the sweet spot. And if you're going to continue to add load, your performance is going to deteriorate significantly. That's the point that you want to add resources, okay? But that shape of the graph really depends on the traffic pattern. If the traffic pattern change, the shape of the graphs change. So how do we know? We have a model tuner that is actually observing the state and tuning the way we're doing the queuing theory so that we can get good results. So this is the ideas that we have. I just want to emphasize, this is the ideas that we have today. We've tested them. We have some good results. There could be many more ideas to explore. So I do want to encourage everyone to go there and work with us, use LLMD, try new techniques, consider contributing them back to the community, and write papers about them, and so on. So yeah, that's my call to join us, and you have the QR code. You can take the repository, join the developer Slack, deploy it, test it, and so on. And we have a lot of calls every week. You can find all the information on the website. I can tell you we have about 7 calls each week. So one of the calls is today, Wednesday at 12:30 EST, and that's our community call, and that's sort of an open stage. Everyone can join, you can ask any question, and so on. And then for each one of these areas that I mentioned, there is a weekly call. KV cache, scheduler, the benchmarking, and so on and so forth, and auto-scaling. Auto-scaling is today at 2 EST, so that means, what's the time? 9 p.m. 9 p.m. I'm going to be on that call today. Anyway, everyone are enjoyed to join. You can join us, you can work with us, you can contribute. I think that's it. I can take some questions.